All right. So we got some viewers here. Today's episode in Flat Earth Falsehoods is going to be all about the lunar phases and the recent lunar eclipse from January 31st. I'm doing this video on the phases of the moon because I've recently been hanging out in the 24/7 Flat Earth Discord. This is the Discord channel on Flat Earth that I think ODD operates. And one of the things I've noticed is that they tend to say that they understand the globe model and then produce a picture or something that shows that they don't actually understand the globe model. So I'd like to start this episode by showing you what they showed me. Okay. Present to everyone. There we go. So hopefully you can all see this. Oops, did I just unshare it? Yeah. Share. Present to everyone. Hide. There we go. Okay, so this image that you see here, I'll even zoom in a bit for you. This is an image I was shown by a guy named Me Morvet. He showed this image to me. He said it demonstrates the phases of the moon that the globe model says we get. And I'm talking to other people on that Discord today, and they say that this is provided to us by NASA, that this is a NASA official image. It's completely incorrect. So he used this image to show me that an observer standing here, for example, noon on Earth, that an observer standing here would be able to see. No. Okay. He was saying an observer standing here, which would be, I guess, like 6 p.m. or so, or 3 p.m., that this is the moon that they would see, or this is a moon that they could see. Whereas, so the part of the moon that they're seeing is not the same as the part of the moon that NASA says we should see, something like that. My point was that this image isn't nearly to scale. That if it was made to scale, they would realize that if it's made to scale, it accurately represents the phases of the moon. So what I'm going to do now is I'm going to show a couple demonstrations of the phases of the moon to scale from Earth. So let me open those up for you. Phases of the moon. Moon phases in the globe model. All right. So first of all, you can see right away the scale that we have to deal with, okay? I have an observer here. I have two observers on the Earth. I have the moon down here. If I zoom in, you can actually see how small the moon is, okay? So that's the moon. I have the moon. We're going to say that the sun is to the right in our image, okay? The sun is to the right. The sun is to the right, so the shadowy portion of the moon is here, and the lit portion of the moon is here. And the same thing goes. The same thing goes for the Earth. This is the Earth. This is the lit portion of the Earth. This is the unlit portion of the Earth. So an observer over here is in daytime, and an observer over here is in nighttime. And we're going to assume these observers are on the equator, okay? The red lines and the yellow lines from the observers indicate their point of view of the moon, what they can see of the moon, okay? So first of all, if we look at these two observers, one of them pretty much at high noon, and one of them pretty much right at midnight. We're going to put them just a little before. Okay. Both of them, at this point, they can see what we would call either a first quarter or a third quarter moon. They see the moon half illuminated. half of what they can see of the moon is illuminated. Okay, so they see a shadowy portion of the moon here and a lit portion of the moon here. And you can actually see, if I zoom in really close, they actually see slightly different halves of the moon's face. And I went over this in a previous week's video, that two observers at diametrically opposed points of the Earth, when they're looking at the moon, they see, I think it's like there's a 3.6 degree difference total of what they see. So 1.8 degrees on this side and 1.8 degrees on this side. You're seeing almost the exact same portion of the moon, but it is very slightly different. And a good experiment that I'm going to do soon, when the weather is good and there's a full moon, is I want to take a zoomed picture of the moon at moonrise when it's full, and then another zoomed picture of the moon just before moonset when it's full on the same evening, and compare what I can see of the moon at moonrise and what I can see of the moon at moonset, and see if there is actually a very slight difference. But anyway, so we can see that both of these observers, where they are, can see the same quarter moon. Okay. Now, when can an observer during the daytime no longer see a first quarter moon or a third quarter moon, whichever it is? I'm kind of bad with that. When he can no longer see it is when his red lines here, the lines of sight, when those lines of sight intersect with the Earth. And my browser is crashing. That's cool. No, that's okay, guys. Just there we go. Okay. Yeah. GeoGebra is crashing on me right now. It's not responding quickly enough. So I'll keep talking. There we go. When his line of sight goes through the Earth again, that means that the moon is below his horizon. So long as the observer is not looking through the Earth, so here he can't see the quarter moon anymore. The only time that an observer can see that particular quarter moon is on this half of the Earth, on this part of his cycle around the Earth. So pretty much the 12 hours it takes for him to get from here to here, give or take, because as we know, the moon is also rotating, the moon is also moving through the sky, so it's not exactly 12 hours. But the point remains that the observer can see that particular quarter moon phase while he's on this part of the Earth. That means he can't see it when he's over here. The only way he could see it if he's over here is if he's up on the North Pole, where he doesn't have to look through Earth. So the same can be said for, this observer in the nighttime. He can't see it when he's here. Okay. So now what I'm going to do is I'm going to move the moon around the Earth. Okay. So this is a quarter phase. This is a waning. This would be waning gibbous. And if I zoom in, you'll see that it is, in fact, no, it's not a waning gibbous. It's a waning crescent at this point. So as it goes around, it's becoming more and more of a crescent. Becoming more and more of a crescent. So let's go to here. Now remember, in my model, the sun is straight out on the x-axis. So this is how much of the moon is lit up that we can see, and this is how much is dark. When can we see this particular phase of the moon? All we need to do is go back to our Earth and make sure both of our observers' lines of sight are not going through the Earth. So we move this guy to about there. We move this observer to about there. And again, you'll see that they're pretty much 180 degrees opposite one another. And this is what we expect. I'm glad that they don't own you. And Nim, thanks for stopping by. And Beach also, you were the first one here. Beach, thanks. All right. So now we get to, if I go back to that first image I showed, again, you'll notice that while the illuminated and dark portions of the moon are correct, the distance from the Earth to the moon, given the size of the moon, is not correct at all. So let's take, for example, this position. Let's reproduce this position. And in order to do that, I'm going to have to, in my mind, and you're going to have to do this too, you're going to have to flip this picture 180 degrees over like this, okay? Because I have my light source coming from here, and he has his light source coming from here. So what we're going to do is we're going to put an observer. We're going to put our observers here, okay? It looks like it's at the 45 degree mark. Yeah. So we're going to go to about 45 degrees. We're going to put both of our observers there. Okay. So they're seeing the same thing. Both of our observers are there. And so the observer here, we want to know what kind of moon they see when the moon is 45 plus half of 45, I guess, degrees away from them. Okay. So let's do that. Let's move the moon there. Okay. So this is 45 degrees away. And these are increments of 30. So that'd be about 15 there. Trying to get it to match. Yeah, because this is 45 and that's 45. 45 plus 22. So if that's 15, we're going to call it about here. Okay. So this is about a representation of this image of the observer standing here, looking at this phase of the moon. Now in the image, they don't own me. After I'm done talking about these moon phases, I will bring up the lunar eclipse and why they criticize the globe model because of it. It's the next thing I'm getting to after I do these moon phases. So we have the moon here. Let me make sure. Yeah, we have the moon here. And we have a person here. Okay. So this is what they see of the moon. They see this portion of the moon. You know what? I think I made a big fuss about this image for nothing. I think, yeah, this actually, apart from not being to scale, you know what? I don't think there's such a big problem about this. Let me get to the real claim that he made, or the major claim that he made, which was that you could see a full moon in midday. Because all this is showing is that, yes, you see a certain portion of the illuminated and non-illuminated portions of the moon. And it depends on where the moon is around the Earth and where you are on the Earth. So when can you see a full moon? And Tada, see, look, I'm honest. I kind of made this big deal about this image. And I'm not going to like hide the fact that I thought it was erroneous or whatever. Just going to keep going. All right, so this is a full moon, okay? Full moon is in this phase here when it's pretty much 180 degrees opposite of the sun, okay? So we have the moon here, and we can see that the dark side of the moon is completely away from us, and the observers are seeing the lit side of the moon, okay? So if we put it right there, when can you see a full moon? Well, if you'll notice, our two observers' lines of sight are going through the Earth, which means from where they are, they can't see a full moon. We would need to move our observers to here and here in order to see the full moon. Now, if the moon is just slightly before or slightly past the full phase, it could still look full to our eyes. And because it's slightly further around in its orbit, our observers could also be slightly further around the Earth. So here we have a person who's just barely in daylight, who's still able to see what looks to him like a full moon. And it might be a full moon. Is there ever a time when a person could be at midday and see a full moon? The only way he could do that is if he's up on the North Pole, uh, or 23.5 degrees. If he is at the topmost point of the Earth, given the tilt of the Earth, then he could see a full moon while he also saw the sun. But if he's on the equator or at these other intermediate latitudes, then no, you wouldn't be able to see a full moon during the day. So if we're going to say that this guy, let's take this guy. So this guy is just coming out of night and into day. In order for him to see what looks like a full moon from about here, we're going to have to move the moon about here. And again, this looks like a full moon to that guy for sure. Like if you zoom in, there's only a very, very small part of the illuminated part of the moon that he's not seeing. It might look like a full moon to him, but it would actually be a gibbous moon. So this is the globe model phases of the moon. Where you are and where the moon is around the Earth depends on what amount of the moon you see, what illuminated portion of the moon you see. Okay, so that's moon phases. Now let's get to the eclipse. So the eclipse, this video here, I'll post it in chat. You can watch if you like. This video claims that the lunar eclipse from the end of January does not work on the globe. That's the title of his video. Lunar eclipse doesn't work on your globe. Okay. So if we watch this, I have it sped up 2 times. If we watch this, we're going to see from his vantage point on the Earth that the shadow on the moon starts from the top of the moon. Hang on, let me address this. Martian NN22. It is possible to see an almost entirely full moon during the day. Yes, it is. What hours of the day? It would have to be right after sunrise or right before sunset. You can't see a full moon at midday, which is the claim that was being made to by Meme Warvet. He also showed me 2 pictures of an almost full moon. I would say it was a gibbous moon, a very close to full moon. He showed me these 2 very full looking moons against a bluish color sky. And I said, well, given the other things that I see in the picture, it looks like the moon is low to the horizon. And it looks like the color of the sky represents just after dawn. I got a timeout for disagreeing with him that those moons were full and they were taken in the middle of the day. So I really want to see pictures of the full moon at midday. If people could provide those for me, I would love to see them. I would love to see pictures of the full moon in the middle of the day taken from somewhere other than the North Pole or the South Pole. I don't think I'm ever going to see those images. So let's get back to this video. Okay, so here we go. We see the shadow on the face of the moon is coming from the top. And this, most flat earthers I've seen do not accept this at all. And he speeds it up and he shows as the moon is setting, the shadow is coming more and more from the top. And he doesn't understand this. And he's going to show you what he thinks it should have looked like. This is a picture, I don't know from where. It's still in his video. Maybe this is somebody else's image. But so what we're seeing here, it's all these pictures. And I believe D Marble shows you what it should have looked like. He inverts it. Yeah, there we go. So D Marbled's video, he basically says, look, if the moon is setting and it's going into the shadow of the Earth, shouldn't the shadow be coming from the bottom up? And again, flat earthers will often tell you, look, I know the globe model and it doesn't work. When they show you this, it means that they don't know the globe model. Here is a representation of the globe model. Martian, if you're asking what program this is that I show these diagrams in, this is GeoGebra. What's the link in chat? So this is a dual look at the Earth-Moon system. If I hide some things first, let me hide these. Okay. So this represents the Earth. Okay, this is the Earth, and this is the moon on its orbit around the Earth and looking sideways on. And you'll notice that the moon's orbit around the Earth is tilted 5 degrees. I've tilted it 5 degrees. That's what we observe it to be. So as the moon is going around the Earth, every now and then the moon, and the x-axis represents the ecliptic plane. The x-axis, oh yes, Malcolm Lamont, you saw the shadow from the bottom up and you live in Australia. I'm going to talk about this because I made an observation last night. I was like, hey, in the northern hemisphere, the shadow started from the top of the moon, and in the southern hemisphere, the shadow started from the bottom of the moon. And I made a guess as to what that meant. I checked, I was correct, and I'll get to this discovery in just a minute. So this x-axis represents the ecliptic. It represents the plane of the sun to us. Okay, so every now and then, the moon is in a line, a direct line between the Earth and the sun. 0 degree deviation. Okay. When the moon happens to be at 0 degrees from the Earth, so the Earth, moon, and sun make a straight line, under those conditions, you can get a lunar or a solar eclipse. A lunar eclipse is when the moon is behind the Earth and directly lined up with the sun. And the solar eclipse is when the moon is in front of the Earth and directly in front of the sun. Okay. So as the moon is going around its orbit, sometimes it's lower than the Earth, sometimes it's higher than the Earth. When it goes from its higher position down to its lower, we call this it passing its descending node. And when it goes from its lower orbit, when it passes up, we call this the ascending node. Okay. Now I'm going to show you the same diagram. This diagram is looking front on. Now I'm going to show you this diagram looking from the top down. So I'm going to remove those. I'm going to add these. Okay. So now we're looking at the moon system, the moon-Earth system from the top down. This is the Earth. We're going to say the sun is up here, and the sun is shining down like this. And this more or less represents its shadow. Now, the shadow of the Earth actually tapers, but for our purposes, I'm not doing that. I'm just showing you that the sun is up here and the Earth casts a shadow this way. So as the moon is going around the Earth, every now and then, its ascending node or its descending node will occur here. Sometimes the node traverse is here. Sometimes the node traverses here. Sometimes it traverses its ascending and descending node over here or over here or over here or over here. And then we don't get an eclipse at all because we're not lined up with the sun and the moon at the same time that the moon is lined up at 0 degree deviation from the Earth's orbit. Okay. But when the moon happens to be here at its ascending or descending node, when the moon happens to be here at its ascending or descending node, those are the times we get an eclipse. Now, for the eclipse, for the lunar eclipse that we saw January 31st, the moon is coming this way around the Earth, or no, I guess the moon's going this way around the Earth. Okay. So the moon gets here and it starts to enter our shadow. Okay. And it enters our shadow like this. So part of it is in the shadow, and then more of it is in the shadow, and more, and then it's totally in the shadow, and we see it red. Yeah, the sun shining down in this representation. We're looking from the top down, okay? So the sun is up here, the earth is here, so the sun is shining this way. It's a 2D representation of three-dimensional space. If I had taken more time, they don't own me. I could have used GeoGebra's 3D system. However, I opted to do it simply in 2 dimensions because it's faster for me to draw it up in 2 dimensions than in 3. Okay. So as the moon enters our shadow, okay. Now remember, it's doing this either at an ascending or a descending node. And again, what ascending and descending nodes means is that sometimes the moon's position is below the Earth, and sometimes it's above the Earth. Oops. Where is the moon? Let me get this moon back. Okay, so there's the moon. Okay. Okay. So as I was saying, so as the moon is coming from its lower orbit to its higher orbit, it's going through an ascending node. Now, when we look, okay, so now we're looking head on again. So we're not looking from the top down now, we're looking head on again. As the moon enters our shadow, an observer in the northern hemisphere looking at the moon, let's say an observer is standing, here. Let me try to get this correct. An observer in the northern hemisphere. That guy's not on the northern hemisphere. Okay. I'll put a guy here. When he's looking at the moon, he sees. Now let me go back to this bit. Go back to no. Okay, so this guy is in the northern hemisphere. The reason he sees the shadow starting from the top is because the moon is going from its descending node to its ascending node, which means that the moon that we see here, even though over the course of the night the moon appears to be going from left to right, we actually know that the moon is rotating around the Earth in the same direction that the Earth is spinning. Okay, so the Earth is spinning this way, and the moon is also going around the Earth this way. We can tell that the moon is going in the same direction as the Earth because we see the moon change its position against the stars over the course of an evening. If you make a star trail, if you take a time lapse picture of the stars over the course of a night, they'll make circles. The moon is going to make its own path among those circles. It's not going to follow the same circular path as any of those stars. It's going to cut across those circles. Hang on a second. I have the phone ringing. Got to shut it up. That was easy. The joys of live streaming. Okay, so let's try to wrap this up because it's already been a half hour and I don't want to make these videos too long. So the the moon is entering the Earth's shadow. The moon is entering the Earth's shadow. The sun in this picture is behind the Earth from us, and the Earth is casting a shadow into space, and the moon is going up into the Earth's shadow, even as you are rotating around the Earth, and even as the moon is moving, like, so the moon is moving around the Earth at the same time that you are revolving around the Earth. Yeah, I'm trying to do that right now. They don't own me. Like, I'm explaining why. Okay, so all right, so maybe I'm talking too much. So what flat earthers said about this eclipse is that the shadow on the eclipse should always be on the bottom. Okay, um, because they think that the shadow that the Earth is casting is, for all intents and purposes, straight ahead of you. Like wherever you're standing on the Earth, they think that if the sun is making the Earth cast a shadow, it's straight in front of you. Um, in reality, the shadow that the Earth is casting is somewhere into space, and we can tell where it is in space because the moon, as it's going around the Earth, here the moon is going up into our shadow. Um, okay, so as the night progresses, it looks like the moon is going down. It looks like the moon is setting. That's because the Earth is spinning, and the moon. Okay, so I really should have done a 3D model. Um, Oh, let me go back to my other model. Let me go back to my other GeoGebra model and show you that again. Okay. Delete, open, phases of the moon. Phases of the moon. Nope, not that one. Or was it that one? Here it is. Okay. All right. So what's happening is the moon is going around the Earth like this at the same time that you are spinning around with the Earth. Okay. So what that means is that when we saw the lunar eclipse, let me move it back here. Okay. When we saw the lunar eclipse, okay, we have an observer in the nighttime. We don't really care about this other observer. Okay. So this observer, he's on the Earth and the Earth is rotating. And so the observer is going like this over the course of the night. Okay. While the observer is going like this, the moon is also going around the Earth. Okay. So we're both going around in a circle in the same direction. The view that this person has of the moon, because they were in the northern hemisphere, okay, the person on the northern hemisphere looking at the moon, because the moon is coming up into the Earth's shadow, they are going to see the shadow on the moon start from the top of the Earth. An observer in the southern hemisphere, like somebody said they were, who said they were in the southern hemisphere? Malcolm Lamont. Okay, so Malcolm, you in the southern hemisphere, your view of the moon is essentially upside down from our view of the moon in the northern hemisphere. So you're looking at the moon, essentially to us, upside down. And that's why you see the shadow coming from the bottom of it up. If you were able to move fast enough on the Earth that you could have gotten from Australia up to, say, New York or at least China, you would see your view of the moon changing. But so what you're seeing, so what we're seeing when the moon enters the shadow of the Earth is, what was that? Oh, so because of the direction that the moon is coming from its lower to its upper orbit, so it's going through its ascending node, because it's going up into the Earth's shadow from the northern hemisphere, we see that as the shadow starting from the top of the moon. Now, If this had been its descending node, then in the northern hemisphere, as the moon enters the Earth's shadow, we would see the shadow on the moon start from the bottom of the moon up. And I decided, I came up with this yesterday. I was like, oh, I get it. So in the northern hemisphere, we saw the shadow on the moon start from the top. That would make sense if the moon were going through its ascending node. So I went to this website, AstroPixels, and it shows you node passages of the moon from 2001 to 2100. Okay. Ascending node date and time is on the left. Descending node date and time is on the right. So I go down to 2018, January 31st. January 31st, the moon went through its ascending node. And the T here represents that there was a total lunar eclipse at that time. Okay. So that's pretty much what I wanted to go over today. The flat earthers that say that they understand the globe model and then say that the lunar eclipse shadow starting from the top of the moon disproves the globe model shows that they don't actually understand the globe model. The globe model is tricky because it requires three-dimensional thinking. It requires you to be able to imagine in 3 dimensions or to come up with a decent 3-dimensional model. In my case, I didn't come up with a 3-dimensional model. I came up with two 2-dimensional models. Maybe I'll do another episode in a couple weeks when I've made a 3D model of this and show you how, for an observer on the northern hemisphere for this eclipse, the shadow should be coming from the top down, just like an observer in the southern hemisphere, like Australia, they saw it coming from the bottom up. There will be an eclipse in the future. Let me find the next total lunar eclipse. Okay, July 27th, there will be a total lunar eclipse, and the moon will be going through its descending node. What that means is that people in the northern hemisphere, they will see the shadow start from the bottom up. And people in the southern hemisphere, they will see the shadow from the top down. Beginning of 2019, there will be another total lunar eclipse during the ascending node. And this means that observers in the northern hemisphere will see the shadow start from the top down, and observers in the southern hemisphere will see the shadow begin from the bottom up. All right, it's been a half hour. It's been 40 minutes, actually. Thank you guys for your attention and your conversation in the chat. Thank you, Malcolm and Martian and Keith. And You Don't Own Me or No One Owns Me. What was it? And Richard Ski, They Don't Own Me. Beach, Nim, thanks for coming by. Also, you guys know I don't ask for money. I'm not on Patreon. I don't ask for tips. These are low budget, low production videos. David Murphy, thank you for coming by. In the future, I'll probably make non-live videos that are higher production quality. But again, I'm not going to ask you for money. I'm not going to monetize because I don't need money from this. Sean, you can watch the replay. I'm just doing this. I'm putting out a video every week with 1 or 2 related topics slowly to try to combat the misinformation out there in the flat earth community about the globe model. Because really what it comes down to is they either don't understand the globe model or they are misrepresenting the globe model. Thank you again for stopping by. Have a good rest of your day.